Hello, welcome back to this. Well, it's becoming an informatics channel, I guess. Today we're talking about one of the problems, another problem from this year's bio final, which is pirates, and I'm joined by Andrew Park, who is one of the top competitors this year. And yeah, it's a pleasure to have you, Andrew.
I am very honored.
Yeah, so we'll be talking about pirates today. So yeah, Andrew solved pirates. And he had a particularly nice solution. So I'm going to talk you through the problem, and then Andrew will talk you through his solution. So let's get right into it. This is the problem statement, but we'll do it on a whiteboard. So yeah, let's get into it. So in this problem, the statement isn't too complicated. We've got a bunch of points in the coordinate plane with given coordinates. So let's say these are our points. I don't know if you can see where I'm drawing, Andrew. It's just somewhere in the middle of the whiteboard. Cool. So yeah, we've got a bunch of points, and then some rectangles, and then for each rectangle, the question is how many of the given points are in the rectangle. So the format the rectangles are given in is just like two of the corners of the rectangle be provided, and then that defines the rectangle. So for this rectangle, the answer will be 2. We might have another rectangle like this. And the answer will be 3. And so that's how it's given. Wait a minute. Wait. How does the coordinate system work again? So are the points in the cells or are they on the edges? They should be in the cells, right?
I think it's inclusive. Like on the edge is fine. It still counts.
Yeah, so the rectangles are from a point to a point. Yeah, cool. All right, just making sure. So yeah, this point would be counted as in this rectangle. So I mean, if the coordinate system was like this could be, 0, 0 could be in this corner. That's a really bad drawing. But imagine this corner is 0, 0. So this point here would be 3, 1. And so on for all these points. And the rectangles are given from point to point, and it's inclusive. Yeah, so for each rectangle, we want to count the number of points inside. So in this case, the first rectangle has 2 and the second one has 3. So yeah, when we need to do that sort of efficiently. So the number of points can be up to 2 to the 12. So that's around 4,000. And the number of rectangles can be up to 2 to the 20, so that's around 1 million. And the points and the coordinates themselves are from 0 up to, some very big number, 2 to the 31. So yeah, that's the problem. This is my code. That's not what I meant to do. This is the whiteboard again. So yeah.
Great.
Over to Andrew.
Before we solve this problem, I think it's worth going over 2D prefix sum, how it works. So, okay. Suppose, wait, it's very thick.
Whoa. Yeah. Let me.
Very thick. I guess that's acceptable.
Yeah, it's fine.
Yeah. So suppose you have like a 2D binary grid. So like each grid is either 0 or 1. And you're given a rectangle just like in the question, and you want to count how many ones are in the rectangle. So you want to get the sum of all the values inside that rectangle. So, for example,
So each of the cells has a 0 or 1 in it.
yeah, so it's like a binary
Sure.
grid. So each of the cell has either a 0 or 1. So suppose you want to get this rectangle.
Yeah.
It would be better if I label. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6. That's J, that's I.
Okay.
Yeah. So if I want to get that rectangle, that's the same as getting this rectangle and then minusing this rectangle and this rectangle and then adding in this rectangle because it's been subtracted twice. So basically what that would look like is this rectangle is the same as this rectangle minus this rectangle minus this rectangle and then plus this corner. And okay.
Yep.
So if we say this is y1 x1 y2 x2, then this is 0 0 y2 x2 0 0 y2 x1 minus 1 0 0 y1 minus 1 x2 and then 0 0 y1 minus 1 x1 minus 1. So as you can see, if we basically have access to a function, say f of y x, where this returns the answer for this particular grid. So with 0 0 at the left upper corner and then yx at the bottom right corner, then we can get the answer for y1 x1. We can get the answer for this rectangle as f of y2 x2 minus f of y2 x1 minus 1 minus f of y1 minus 1 x2 plus f of y1 minus 1 x1 minus 1. So if we can basically have these values computed in efficient time, we can get any sort of rectangle using this formula.
So you're saying if you have the answer for if you can compute the answer for a simplest type of problem, which is like any rectangle starting at the top left corner, then you can use a combination of those to compute any rectangle.
Yes.
Yeah.
Yes.
So that's pretty cool.
Yeah. So to do that, okay, we can think about like a 1D problem, 1D version of the problem. So if you have like this is 1D prefix sum. So if you have a 1D binary array, again, so each element is 0 or 1. And let's say you're given like two integers L and R. And then you have to figure out like the sum of the integers within this boundary, and you want to do this efficiently, then you can do this by working out cumulative sum of the original array. So that would look like 0, 1, 1, 1, 2, 2, 3. And then let's say we call this array sum. And then the answer will just be sum of R minus sum of L minus 1, which makes sense. So if you want to expand this to 2D,
yeah, because here you're
2D.
subtracting, like, whoa, why can't I draw?
Yeah, so it makes sense because you're basically getting this sum, and then you're minusing this sum, so you're left with the desired region.
Thanks. That's exactly what I tried to draw.
Yeah. So for 2D prefix sum, we can expand this idea, and okay, let's say we have. I'm going to draw the grid again. And just fill it with random arrays. We can first do 1D prefix sum on each row. So each row will become like a cumulative sum.
Yeah.
0, 0, 1, 1, 0, 1, 2, 2, 1, 2, 2, 3, 1, 1, 2. And then you can do a prefix sum on the columns, so you can go like vertically. One, 3, 5, 6, 1, 2,
Sorry,
6.
I don't know what my editor is doing here. I'm just trying to move. There we go.
All right.
Yeah, so you did the horizontal sums,
Yeah.
like you did in 1D, and then you did them vertically once you'd done that. Cool.
Yeah, and as some of you might have noticed, this gives you that function f of yx. Like if you look in this square, which has 5, that basically says in the original grid, this region has 5, the sum of 5, because it has 1, 2, 3, 4, 5 ones. And this works because basically the recurrence relationship for this function f of yx is just f of y minus 1x, and then you add the prefix sum for the row y until x. So basically this rectangle is just, if you have the answer for this rectangle, and then you have the answer for this individual row prefix sum, you can just add these together to get the bigger one. And this is how this recurrence relationship shows that. And this value is already computed in the first step when you add the horizontal prefix sum. So when you add it vertically after that, this is basically what it computes. So in total, the time complexity for computing this function for all y's and x's will just be O of n times n, where n is the number of rows and n is the number of columns.
Yeah.
Which is, yeah.
Cool. So that's prefix sums. So now we have to, I mean, it sounds like it would be useful for this problem. So how are you applying it to this problem?
Yeah, so it's useful because this is literally like in the problem we're given like this, and then we're given like a rectangular area and to count up how many points it's in there. But the problem is we can't do this naively in this problem because well, as Erekli has already mentioned, the coordinates are between 0 and 2 to the 31.
Yeah.
Which is around like 2e9. So if we just do it naively, this would be like 2e9 times 2e9 in the worst case, and that's 4e18, and that's way too big.
So if you do this, if you take the whole coordinate system just as your grid, then this is not going to work because there's just too much.
Yeah. But we can solve this problem by compressing the coordinates. So if we have a look at one of the samples for this question, I can paste the text. Just this. It's basically saying that there is a grid. Let me draw the grid. Say there is a coordinate system like so.
So there are 3 points and 2 rectangles in this example.
Yes, there are 3 points, and so it will be like, let's say 10 is here, 10 is here. So there's a point here, 20, 20, and then 5, 25. So these are like the points. You can actually notice that all the values between like 10 and 20, so from 11 to 19, are actually not relevant at all because they don't. And like same with 21 to 24, and also 0 to 9, they're not actually like useful because like this is all just wasted space. There's no events happening. There's no like point there. It's like sort of irrelevant. Like only like these given points, only those matter when you're computing the answer. So what you can do is relabel, sort of. Let me write this out. You can relabel, so
yeah.
Let me choose a different color as well.
So you're only keeping the relevant points.
Yeah, so I'm only keeping the relevant points. So this will become 1, 2, 3, and then this will become 1, 2, 3. And so as you can see, if we just compress the coordinates into how many like distinct of them there are, because there are at most p of them, and p is the number of coordinates given in the question, and that's up to 2 to the 12, right?
Yeah, up to 2 to the 12 points.
Yeah, so that up to 2 to the 12. So this will be at most of p squared, which is 2 to the 24, which is around 2e7, I think. So that runs fast enough. So we just need to compress the coordinates and then do prefix sums on them. But there is a subtle catch, which is there is a quite subtle catch, which is if you okay, let's just go with the sample. So in the first query, you have 21, 21 in the bottom right corner, so here.
Yep.
And then 7, 7 in the upper left corner. So
yeah, that's got 2 points in it.
Yeah, so that's the rectangle defined by that query. You can actually see that for the, I'll write it down. So for the bottom right corner, we want to find the closest relevant yx where y is less than 21 and x is less than 21. And for the upper left corner, we want to find the closest relevant yx where y is greater than 7 and x is greater than 7. So if we apply these two rules, so let's apply the first rule first. What will that look like? So, for example, this bottom right corner will get shifted to here because this is the closest relevant point that is from the bottom right corner. So you can actually shrink the rectangle into this region, and that would still give the same answer because we've basically skipped all the spaces that are relevant, and this will still this wouldn't change the answer at all. And same with the upper left corner, you can shrink the region again into let me choose a different color.
I see. So the issue that you faced is that you have the points now with compressed coordinates, but the original rectangles you had are still using the original coordinates. So you need to somehow convert them into compressed coordinates, but they're not. They might not directly correspond to compressed coordinates.
Yeah, so they don't directly correspond. So I need to find the closest relevant point where that is compressible, and then after we convert them, we can compress them back. We can compress them. So yeah. Does that make sense?
Yeah.
So that's it really. So to give you a rundown, you basically, for this question, you just need to you need to compress the coordinates. And then for each query, you need to perform a binary search because basically to find these two conditions, this is just like a binary search. One is the upper bound, one is the lower bound. And then you just answer the queries afterwards.
Yeah. So you're answering the queries online.
Yes, online.
Which means
there are no modifications.
Yeah. And then also, so your closest relevant point here, that point doesn't actually have to be one of the given points in the input, right? It just has to be the y has to be one of the y coordinates of a point in the input, and the x has to be as well, but not necessarily the point itself. Cool.
Yeah. Have I missed anything?
No, that sounds good. Yeah.
Great. Okay. Shall I screen share so I can show my code?
Sure, yeah. Before you do, actually, so one of the other ways you could get around this closest, the fact that the rectangles themselves are not in the compressed coordinates, so you have to do this search, is you could also put the rectangle's coordinates in the compression, in the coordinates to be compressed, and count them as relevant coordinates too. Although I haven't tried that for this problem, and the number of points here is quite high, so I'm not actually sure whether. Oh wait, so the number of rectangles here is massive, isn't it?
Yeah, so there are so many queries where if you compress every single one of them, it's it doesn't work, I don't think.
Yeah,
that's why I tried initially.
Yeah, good point. Yeah, so I think that wouldn't work here.
I think binary search is the only way to do this problem. I think.
Yep. Yeah, that's a good way of doing it. So yeah, go ahead and share your code.
Yes. So I actually switched to Visual Studio Code after the contest. So I had Visual Studio Code open for the whole thing, and that drained the battery. So it's a very questionable laptop.
Oh, what were you using before that? Oh, you said you were using Notepad++ in the
Yeah,
class.
so I was using Notepad++. I switched to VS Code because I saw like Boris doing debugging, like setting breakpoints and stuff, and like that is so much convenient than like whatever I was doing.
Yeah.
So that's why I switched, and it's been very helpful. So it just drains my battery very quickly.
Yeah. No,
Right.
that's fair. Thanks.
Okay, so this is my code. We'll go through each function separately. So firstly, the solve function um, takes in the input, so how many coordinates there are, and yeah, how many like treasures, so how many dots there are in the Cartesian plane, and then the number of queries, and then I call the procedure compress. This takes in the input, and then this line just makes so I add x's. So I add all the x coordinates to the vector x's and do the same for y's. And then this code just make the x's and y's sorted and all the elements become distinct. So there are no repeated elements. And then I just do compressing here with the map and then like a pointer. After that, so I do the prefix sum thing here. And then in the queries, I take in the coordinates, and because the problem doesn't actually state like which corners they give you, I do a little bit of swapping and inequality to make sure x1, y1 is the upper left corner and x2, y2 is the bottom right corner. And then after that, I convert these x1, y1, and x2, y2 into compressed forms by finding the closest relevant points through binary search. So you see find upper and find lower. This is just a very standard upper bound and lower bound finding functions. You can also do this with like the built-in like std upper bound, but I prefer to write mine out. And then after that, you pass these new converted coordinates in the compressed plane into the function calculate. And then this is basically, we've discussed it during the whiteboard. So that's what it does. And that's really it. Yeah, that's it. Can I talk about some like common pitfalls?
Yeah.
Because
Go
a
ahead.
lot of people like time limit exceeded on this problem, even though most were able to solve it. So
Oh yeah. So even though this was, I mean, it was one of the most solved problems.
yeah,
But also, yeah, it was quite. I think some people really struggled to hit the time limit, even though they had a solution that was right.
yeah. So one pitfall was they weren't using fast IO.
Ah.
Yeah. So I think some of the time limit exceeded was because they weren't using fast IO because they assumed like file inputs, so like you wouldn't need it, but this actually helps. And then the other one was when they were compressing the coordinates, they were using sets, which they were using set, and then they were like they were inserting into set after each input, which is technically the same time complexity, but
Yeah.
it's a lot slower. It's a lot slower than like inserting all into a vector, sorting it, and then removing the duplicates because sets are quite slow. So there was that, and then another one was one person was using set, and then they were using the std like lower bound like that, but
In a vector. Yeah.
no, someone was using this in a set, which which is linear time actually. So you would think this is like log n, because this is supposed to be binary set, but it's not, because sets iterators are bidirectional. So you can't just access a random iterator. You have to like increment and decrement. So this is actually the same as linear search. This is very slow. What you should be doing instead is x dot lower bound and then the value. That's
Oh, right. I see what you mean. Yeah, I was about to say that's the lower bound notation for a vector, but yeah, I see.
Yeah.
So they were using that on a set.
Yeah. So like some people had this problem, and then some people had a combination of these problems. Yeah.
Cool. Yeah. Yeah. Nice. Your code was, I must admit, your code was, I think, the cleanest code I saw for this problem, or for any problem that any code that passed, actually. So yeah, Andrew gets the unofficial award for cleanest code. Yeah, well explained. It's, I think, the main solution to this problem.
Yeah. Thank you for having me.
Yeah, of course. I'll mention the solution I wrote as well. Do you want to stick around for that, or?
Yeah, sure. Yeah.
Yeah, I mean, you can. Sure. Yeah. We're back on the whiteboard. So, like I said, well, I haven't actually mentioned this, but I had the pleasure of being an organizer, or helping out in the organizing for this competition. So, I saw the problems beforehand, had to test them. I actually misread this problem and didn't read the constraints. So I sort of used a sledgehammer to crack a nut here, in a sense, when I was testing this problem. So my code was a bit longer, and it used some unnecessary stuff, but I think it's still useful to know the technique I used. So I'll just mention it as well. So my solution works like this. So the points you're given, I'll just move back up to the top, actually, where we had an example.
Yeah.
So over here on the topmost diagram. So we're given some points and some rectangles. Same way Andrew did, I'll end up compressing these points as well. The coordinates for these points. But so the way you can go through these is, again, with a similar technique to prefix sums, but doing it online. So if we say that, this rectangle here, the middle one with 2 points in it, the purple one, that's actually equal to this big one down to, coordinate 0 minus this smaller one. I mean, we can do this again and turn it into 4 rectangles, but this is actually enough. Then we can calculate the sum of values in these rectangles. So the number of points in each of these two, the black one and the red one. We can do that without pre-computing like the prefix sum data structure that you have, but we can only do it once in the sense that we have to know all the queries beforehand, and we just go through them in one pass and do it offline. So we take all these rectangles, all these purple rectangles that I've drawn, we decompose them into 2 rectangles like this, each. And then for each pair of these rectangles, if we knew the answers to these, then we'd know the answers to the purple one, like you said. Mm-hmm. So now if we had R rectangles initially, now we have 2 R rectangles as queries, but they all start on the left border at coordinate 0. Mm-hmm. And now, so over here, and now we'll go through from left to right, and we'll go through left to right, and then every time we hit a certain like x coordinate, we'll answer all the rectangles at that x coordinate. And we'll do that by maintaining a data structure that can tell us like the answer for a certain set of y's, a certain range of y's. So I won't go too much into how Fenwick trees work or segment trees. You can use either here. But essentially, they are like a prefix sum data structure, a one-dimensional prefix sum data structure, but they allow you to update live as well. So we'll have a Fenwick tree or a segment tree on this vertical axis, just storing where we can update by adding a point at a certain height, by adding 1. So when we hit this point, we'll add 1 at that height. And then we can also query for any range how many points, I don't know why I drew this so long, but for any range, how many points we've seen in this range. So that means we'll start adding points. We'll add this point here, so we'll add 1. Then we'll add this point because we're going left to right. So we'll sort the points, go left to right, add this point. But actually, before we add this second point, we see this black rectangle ends at this x coordinate. So we'll answer the black rectangle by querying in this range that I've drawn. And this +1 won't have been added yet. So actually, it'll just be 0 for this black one. So we'll write 0 in here. Then we'll add 1 for this point. Then imagine this purple rectangle, this one rectangle was the only one in the query. Then we'll add both these points as well, so +1, +1 at their heights. And then we'll hit the right endpoint of this rectangle, so we'll ask for the red rectangle. And that'll be this range again, and now it has 2 points. And then at the end, we'll do 2 - 0 to get 2 points for this purple one. So yeah, I've said that a bit vaguely. I won't go into the details because it can, if you haven't seen a Fenwick tree before, it can get a bit complicated. But if you know what it is, then that's the solution. Yeah. So I'll link my code for that in the description as well, in case you're interested. Cool. So yeah. Thanks for joining me, Andrew. How's everything going for the? So Andrew qualified for the Western European Olympiad because he did well here in the bio final. So best of luck for that. How are you preparing?
I'm just math solving a lot of Codeforce's questions. Yeah, just solving a lot. Yeah.
Cool. Yeah. Best of luck, and
thank you.
Thanks for joining me.
Yeah, thank you for inviting me. Thank you.
Cool. See ya.
Bye.
Yeah. Okay. I guess that's it.